The heat is relentless, a thick, heavy weight that settles over the valley like an oppressive, wet blanket. It is 95 degrees Fahrenheit. The humidity is locked at 90%, and inside the house, the air is completely motionless. Outside, the steady, high-pitched scream of a diesel generator struggles under the immense electrical load of a conventional air conditioning compressor. Every hour of comfort is bought with gallons of expensive fuel and the constant threat of a system blowout. This is the ultimate off-grid dilemma. But beneath your feet, just 6 feet deep in the dark, damp clay soil, lies a silent thermal reservoir. The ground down there is a steady, quiet 55 degrees Fahrenheit, and it remains that way year-round, completely untouched by the blazing summer sun above. It sounds incredibly simple. You bury a long, inexpensive plastic pipe in the earth. You run a tiny, low-draw fan, and you pull that cool, subterranean air directly into your living room. A mechanical-free, compressor-free air conditioner that runs on pennies a day. But as you slide a digital thermocouple probe deep into that underground run, the numbers on the screen tell a different story. Imagine this. Thousands of homesteaders have tried to replicate this exact setup based on viral internet tutorials, only to discover a silent, hidden failure point. If you build this system without understanding the strict laws of fluid dynamics and soil science, that buried tube will not cool your home. Instead, it will slowly fill with stagnant, warm water. It turns into a dark, damp breeding ground for anaerobic bacteria and toxic spores. And under the right conditions, the pressure imbalances can even cause deadly carbon monoxide to pull backward down your wood stove chimney. We call this the dewpoint trap, the exact physical limit where a cooling pipe ceases to be an air conditioner and becomes an underground puddle. Before we unpack the real physics of these earth-air heat exchangers, and before we look at the actual thermal data from our own installations, I would love to know where you are watching from and what kind of environment you are trying to tame. Take a moment to subscribe to the channel and drop a comment below telling us your location and your current local weather. Whether you are dealing with the dry heat of the desert Southwest or the swampy moisture of the deep South, your local climate changes every single calculation. Let us see how the science holds up in your neck of the woods. Here's what everyone missed. When we look at the history of passive geothermal cooling, we are often pointed to a single, legendary story. If you search the dusty corners of the internet, you will eventually find reference to a man named Jacob Stoltzfus, an Amish farmer living in Lancaster County, Pennsylvania, in the year 1881. The story goes that Jacob, tired of the oppressive Pennsylvania summers, buried a network of salt-glazed clay pipes deep beneath his farmhouse, using the natural drafts of his cellar to pull cool earth air into his living quarters. 1. It is a beautiful image. A 19th century pioneer outsmarting the modern energy grid with nothing but baked clay and human ingenuity. But as historical researchers and safety auditors, we have to ask a difficult question. Is this story entirely true, or have we let a romantic homesteading myth replace real engineering history? When you dig into the archives of Lancaster County and examine early agricultural extension records, you find that the reality is far more nuanced. The plain communities of Pennsylvania and the wider Appalachian region did indeed possess a profound, hands-on understanding of thermal mass, but they rarely used underground pipes to cool their active living spaces. Instead, their engineering was focused on preservation. They built spring houses, structures positioned directly over cold, flowing water, and deep, stone-walled root cellars, with natural dirt floors. These cellars relied on a concept called breadth-of-floor ventilation. The damp, cool earth would absorb heat from the air, while small, carefully placed foundation vents allowed warm air to escape, creating a gentle, natural draft. This passive cycle was highly effective for keeping butter, cheese, and root crops from spoiling during the humid months of July and August. It worked because the structures themselves were drafty, uninsulated, and constantly breathing. The air was in a continuous state of slow, natural exchange with the outdoor environment. Consider that. The historical systems worked because they were open. They did not try to force cold air into a sealed box. When modern builders try to copy this using buried clay pipes, they face immediate structural failures. Antique salt-glazed clay pipes are brittle. Over decades, the subtle shifting of the earth, heavy farm machinery driving overhead, or the expansion of freezing water in the upper soil layers will crack the clay joints. Once a clay joint leaks, the surrounding groundwater seeps in, carrying dirt, silt, and organic matter with it. The clean air duct quickly transforms into a subterranean canal of decaying matter, completely ruining the air quality of the home above. Today, we try to take those same 19th century concepts and force them into 21st century structures. Modern homes are built to be airtight envelopes. We use heavy insulation, house wraps, and high-efficiency windows to trap conditioned air inside. When you take a passive earth tube and hook it up to a highly sealed modern home, you completely alter the pressure dynamics. Without a massive, constant escape path for the air, a passive draft cannot establish itself. If you force the air in with a high-powered fan, you build up positive pressure, and if you pull it out, you create a powerful vacuum. This brings us to the core thermodynamic mechanism that makes earth coupling possible in the first place, the phase shift. To understand the phase shift, we have to look at the earth not as a source of endless cold, but as a giant thermal battery that operates on a massive time delay. The top layer of soil is directly affected by daily weather patterns, but as you dig deeper, the earth begins to act as a low-pass filter, smoothing out the extreme temperature swings of the seasons. By the time you reach a depth of 6 to 8 feet, the soil no longer reacts to the daily sun or passing cold fronts. Instead, it responds to the average temperature of the entire year. This creates a seasonal lag, a physical delay of several weeks or even months. At a depth of 6 feet, the thermal lag is typically 6 to 8 weeks. At 8 feet deep, that delay stretches to nearly 12 weeks, a full 3 months. The warmth of the midsummer sun takes months to conduct through the dense soil. By the time that heat energy reaches 8 feet deep, winter has already arrived at the surface. Conversely, the deep chill of January does not penetrate to that depth until the following summer. When you tap into the earth at this depth during a blistering heat wave, you are literally harvesting the residual cold of the previous winter. It is a beautiful, elegant loop of physics, but it is not a magic, infinite resource. Reflect on that. If you run warm air through a buried pipe continuously, you are constantly depositing heat into the soil immediately surrounding that pipe. Soil has a specific rate of thermal conductivity. It can only move heat away from the pipe wall so fast. If you run your fan 24 hours a day, you will eventually saturate the earth directly touching your tube. The soil temperature will rise. The thermal gradient will shrink, and your cooling effect will steadily decay until the system is barely tempering the air at all. This is why material selection and soil type are so critical. Different soils handle heat transfer in vastly different ways. Dense clay, for example, has excellent thermal conductivity. The moist, tightly packed mineral particles can absorb and move heat away from your pipe far more efficiently than loose, dry sand. But clay also presents a massive engineering hurdle. It expands when wet and contracts when dry, putting immense physical stress on buried pipes. It is also highly impermeable, meaning any water that finds its way into your trench will pool around the pipe rather than draining away. Sand, on the other hand, allows water to drain away effortlessly, reducing the risk of a flooded pipe. But dry sand is a terrible thermal conductor. The tiny air gaps between the sand grains act as insulation, preventing the heat from your pipe from dissipating into the wider earth. If you backfill your trench with the wrong material, you can accidentally insulate your cooling system from the very earth you are trying to harvest. Every single choice, from the depth of your trench to the composition of your backfill, determines whether your system will function as a sensible heat exchanger or fail as an expensive underground mistake. The old-timers understood these limits. They did not try to build systems that defied the local climate. They adapted their lifestyle to match the natural cycles of the earth. If we want to bring this technology into the modern era, we must do the same. But we have to use the rigorous tools of modern physics to do it safely. If you stand on the slope where we broke ground, you can feel the warmth of the summer sun radiating off the weeds and dry grass, a brutal heat that bakes the topsoil until it cracks. But to build a system that works, we had to start not with a shovel, but with a rigorous soil test. We dug a test pit 3 feet wide and 8 feet deep, slicing through the top layers of organic loam down into the heavy, dense clay subsoil. As you scoop up a handful of that deep subsoil, it feels cold, heavy, and slightly damp. This is our thermal medium, the material that will determine how well our system can absorb heat. Many amateur builders make the critical mistake of digging a shallow trench, say 3 or 4 feet deep. They do this because digging deep is hard, expensive, and dangerous. At 3 or 4 feet deep, the soil is still highly volatile. It is directly influenced by the summer sun and winter frosts. If you bury your pipe in this shallow zone, your system will fail. During a July heat wave, the ground around your shallow pipe will already be 70 or 80 degrees Fahrenheit, offering almost no cooling potential whatsoever. To reach the stable geothermal zone, where the ground holds a steady 55 degrees Fahrenheit, you must commit to a trench depth of at least 6 to 8 feet. At this depth, the soil behaves like an entirely different climate zone, but operating a mini excavator at these depths requires immense care. The yellow tracks of our 5-ton excavator groaned as we clawed through rocky clay, carving a trench that was as straight as a laser line. The sides of the trench stood like smooth, cold walls of earth, smelling of damp minerals and ancient buried clay. Now we must address a critical physical requirement that many DIY tutorials completely ignore: the anti-condensation gradient. When warm, highly humid air is pulled from the surface into an underground pipe, it undergoes a rapid temperature drop. As the air cools, its capacity to hold moisture decreases. The water vapor suspended in the air reaches its dew point and condenses into liquid water on the cold inner walls of the pipe. This is not a minor phenomenon. During a humid summer week, a system like this can extract several gallons of water from the air every single day. If that water has nowhere to go, it will pool inside the pipe. It creates miniature, stagnant subterranean lakes. Within weeks, those warm, dark pools will become breeding grounds for mold, mildew, and anaerobic bacteria. Every breath of air pulled into your home would have to pass over this toxic water, ruining your indoor air quality. To prevent this, we established a precise, continuous downward slope of exactly 2%. Over our run of 100 feet, a 2% grade translates to a physical drop of exactly 24 inches or 2 feet. This means the pipe must start 6 feet deep at the intake and gradually descend to 8 feet deep at the foundation wall. To achieve this, we relied on a self-leveling, rotary laser level mounted on a tripod at the edge of the trench. The digital receiver clamped to our grade pole chirped continuously, guiding our excavator operator and hand shovel crew to shave the bottom of the trench down to the exact fraction of an inch. We laid a solid bed of washed river gravel along the floor of the trench to create a stable, non-shifting foundation for our pipe, ensuring that no low spots or bellies could form over time. Let us talk about the pipe material itself. Go to any home improvement center, and you will see giant, inexpensive rolls of black corrugated drainage tile. It is cheap, it is flexible, and it is the absolute worst material you could possibly bury for a cooling system. The corrugated ridges on the interior of those pipes act as thousands of tiny dams. They hold on to condensation, preventing it from draining away even if you have a perfect slope. Furthermore, those ridges create immense aerodynamic friction, disrupting the airflow and making it incredibly difficult for a low-power fan to move air through the system. Instead, we chose 6-inch, smooth wall, Schedule 40 PVC. It is rigid, incredibly durable, and has a glassy, ultra-smooth interior surface that allows condensation to slide down the slope effortlessly. Assembling these heavy 10-foot sections of pipe in the bottom of a 6-foot trench is physically demanding work. The chemical smell of the purple primer and gray PVC cement was heavy in the morning air as we joined the sections together. Each joint was primed, glued, inserted, and held with a quarter-turn twist to ensure an airtight, watertight seal. If a single joint leaks, the surrounding groundwater can seep into our clean air channel, carrying sediment and surface contaminants with it. As we began dry-fitting the pipe runs in the trench, we encountered our first major aerodynamic bottleneck, and this brings us to our first critical engineering layout mistake. If you place a single 90-degree elbow in your underground run, you can restrict the airflow so severely that your inline fan will burn out within a few short weeks. A sharp 90-degree turn creates massive air turbulence. The air molecules slam into the outer wall of the bend, creating a high-pressure zone that acts like a physical wall, choking the flow and causing a major drop in static pressure. We resolve this by using only sweep bends, gentle 45-degree couplings separated by straight runs of pipe. By using two 45-degree bends with a short straight section between them, we allowed the moving air to transition smoothly around corners without losing its momentum. This resistance is what ventilation engineers call the static pressure penalty. Think about that for a second. Every foot of pipe, every joint, and every microscopic imperfection on the inner wall of your tube creates friction against the moving air. If your fan has to fight against too much static pressure, the volumetric flow rate, measured in cubic feet per minute, drops to almost zero. You could have the coldest underground pipe in the world, but if your fan cannot push the air past the static resistance, your home will remain hot and stuffy. We calculated that a 6-inch pipe would allow our fan to move 250 cubic feet per minute with minimal static resistance, requiring only 35 watts of solar-generated power to run continuously. At the absolute lowest point of our underground run, right before the pipe turns upward to enter the crawlspace of our home, we engineered a specialized condensation collection chamber. We buried a heavy-duty, watertight vertical sump basin beneath the main run. The main cooling pipe passes directly over this basin, with a secure, sloping T-fitting that allows all condensed water to fall directly down into a gravel leach field beneath the frost line. To ensure that no subsurface water could back up into our air pipe, we installed a mechanical backflow preventer and a small, low-voltage automatic bilge pump inside the basin. This pump is wired directly to a float switch. If the condensation level rises to a critical point, the pump activates silently, lifting the water out of the basin and discharging it safely to a surface drainage swale far away from our foundation. Finally, we wrapped the entire underground run in a thick layer of native hand-tamped clay. We did not simply throw the excavated dirt back into the trench with a tractor bucket. Doing so would leave large air pockets around the pipe. Air is an excellent insulator. If your pipe is surrounded by air pockets, the heat from the incoming air cannot conduct into the surrounding earth. We added the soil back in thin, 6-inch lifts, using a mechanical plate compactor to pack the damp clay tightly around the PVC walls, ensuring 95% soil compaction and maximum thermal contact between the pipe and the cold earth. It was slow, exhaustive, and meticulous work. But as the last shovel of clay was smoothed over and the trench was completely backfilled, we had constructed a highly stable, subterranean heat exchanger. There were no shortcuts, no cheap materials, and no structural compromises. We had built a system that respected the physical realities of gravity, friction, and thermal mass. With our pipe safely underground and buried beneath a mountain of compacted clay, we have to transition our focus from heavy excavation to the quiet, microscopic physics of heat transfer and the severe atmospheric safety hazards that come with moving air through the earth. This entire system is governed by a fundamental principle of thermodynamics known as Fourier's law of heat conduction. In simple terms, this law dictates that heat will always flow from a region of higher temperature to a region of lower temperature, and the rate of that flow is directly proportional to the temperature difference between them and the thermal conductivity of the materials involved. In our system, the warm, humid outdoor air is the high-temperature zone, and the cold underground pipe walls are the low-temperature zone. As the air passes through the pipe, heat energy naturally migrates out of the airstream, through the PVC pipe walls, and into the surrounding clay. But heat transfer is not instantaneous. Air molecules are poor conductors of heat. They require time and physical contact to shed their thermal energy. This brings us to a phenomenon known as the boundary layer. As air flows through a tube, the air molecules directly touching the pipe walls slow down due to friction, forming a thin, stationary boundary layer. This boundary layer acts as a buffer. If you move your air through the pipe too quickly, say, at a high velocity of more than 1,000 feet per minute, the air molecules in the center of the stream rush through the pipe too quickly to ever touch this boundary layer or transfer their heat. They exit the pipe almost as hot as they entered, completely bypassing the cooling capacity of the Earth. Conversely, if you move the air too slowly, the air cools down quickly, but the overall volume of air delivered to your home is too small to overcome the ambient heat gains of the structure. To find the perfect thermodynamic sweet spot, we must maintain a laminar to transitional flow velocity of exactly 400 to 600 feet per minute. At this speed, the air is moving fast enough to provide a high volume of fresh air, yet slow enough to allow the thermal energy to thoroughly conduct through the boundary layer and into the soil. But as we transition from the underground physics to the indoor mechanics, we encounter the single most dangerous, life-threatening aspect of off-grid home ventilation, a silent hazard that many DIY guides completely ignore. Modern, highly insulated homes are engineered like sealed spaceships. We use thick insulation with R30 walls and R60 ceilings to trap conditioned air. But when you build an airtight envelope and introduce mechanical ventilation, like a powerful fan connected to an earth tube, you completely alter the atmospheric pressure balance inside the living space. Let that sink in. A simple change in air pressure can turn your cozy off-grid retreat into a silent death trap. Imagine a cold winter night. The wind is howling outside, and you have a small wood-burning stove or a propane space heater burning comfortably in the corner of your living room. Under normal conditions, the hot gases from the fire rise up the chimney because hot air is less dense than the surrounding cold air, creating a natural, upward draft that carries carbon monoxide and other toxic combustion products safely out of your home. But now, imagine that your earth tube ventilation system is running. If you have an exhaust fan pulling stale air out of the house without a perfectly balanced, equal supply of air coming in, you will quickly create a negative pressure environment inside your cabin. The house is literally starved for air. It becomes a physical vacuum. Since the cabin is tightly sealed, the easiest path for outdoor air to enter and relieve this vacuum is not through the tiny cracks in the walls, but directly down your chimney flue. The powerful indoor vacuum will pull the air downward through the exhaust pipe of your wood stove or propane heater. This completely stalls the natural draft of the chimney, inverting the flow of exhaust. Instead of rising into the sky, the toxic combustion gases, specifically carbon monoxide, are pulled backward down the chimney flue and dumped directly into your living room. This is what safety auditors refer to as the vacuum effect. It is incredibly subtle. A standard kitchen range hood fan running on its high setting can easily exhaust 400 cubic feet of air per minute. If your home is airtight and you do not have a dedicated, balanced combustion air intake for your heating appliances, that single kitchen fan will immediately invert your wood stove's draft. Suddenly, instead of exhausting dangerous gases, your fireplace is actively importing them. Carbon monoxide is completely odorless, tasteless, and invisible. You will not smell it, and you will not see it. The first symptom of exposure is often a mild headache or drowsiness, followed quickly by loss of consciousness as the gas binds to the hemoglobin in your bloodstream, preventing oxygen from reaching your brain and vital organs. To eliminate this deadly hazard entirely, we implemented a strict, non-negotiable dual-path air balance system. First, we installed a dedicated, sealed outdoor combustion air intake for our wood stove. This is a separate, insulated pipe that runs directly from the outside of the home, under the floor, and connects directly to the air intake of the wood stove's firebox. This means the fire burns outdoor air, completely isolated from the indoor air volume of the cabin. Even if the cabin experiences a sudden drop in pressure, the draft of the wood stove remains completely unaffected because its air supply is mechanically isolated from the indoor living space. Second, we installed an active, balanced ventilation control system. Rather than using a single, unbalanced exhaust fan, we paired our earth tube intake fan with a matched exhaust fan of the exact same capacity. This ensures that for every cubic foot of cool air pulled into the home through our subterranean pipes, an equal cubic foot of stale air is exhausted to the outside. This maintains a perfect, neutral pressure balance inside the home, completely preventing the vacuum effect from ever occurring. Third, we installed a redundant network of multiple, battery-backed digital carbon monoxide detectors. These detectors are positioned at sleeping level, where they can immediately wake you in the event of a failure and directly near our heating appliances. But carbon monoxide is not the only invisible, odorless hazard hiding beneath the soil. We also have to address the silent threat of radon gas ingress. Radon is a naturally occurring, radioactive gas that is produced by the decay of trace amounts of uranium found in clay soils and bedrock. It is the second leading cause of lung cancer in the United States. And because your earth tube is buried deep in the soil, it passes directly through the zone where radon gas accumulates. If your buried PVC pipe has a single unsealed joint, a microscopic crack, or is made of highly permeable material, the natural air currents and pressure differentials can act as a giant straw, pulling radon gas out of the surrounding soil and drafting it directly into your breathing air. To mitigate this risk, we took two critical precautions. We used only heavy wall, Schedule 40 PVC pipes, which are completely impermeable to soil gases, and sealed every joint with certified gas-tight PVC cement. Additionally, before backfilling our trench, we installed a specialized radon barrier membrane beneath the pipe run to redirect any rising soil gases away from our air intake. And finally, we established a strict protocol to conduct a long-term radon test inside our home after the system was operational, using an active electronic radon monitor to verify that our indoor air remained perfectly safe. Designing an off-grid system is not simply about harvesting free cooling. It is about taking full responsibility for the fluid dynamics, the atmospheric pressure, and the chemical safety of the air your family breathes. There are no shortcuts when it comes to the air in your lungs. To truly understand if our engineering decisions were correct, we had to wait for the natural world to put our system to the ultimate test. A dual-season trial designed to push our materials, our physics, and our safety systems to their absolute limits. The first real test came in late July, during a massive, stagnant heat wave that locked over the entire region for 5 consecutive days. The ambient outdoor temperature soared to 98 degrees Fahrenheit, but it was the moisture in the air that made the conditions truly unbearable. The dew point was hovering at a stifling 76 degrees Fahrenheit, creating a heavy, thick atmosphere that made physical labor almost impossible. In a conventional home, this is where the mechanical air conditioning compressors are screaming, consuming thousands of watts of grid power and straining generators to the breaking point. But in our off-grid home, the conventional cooling systems remained completely silent. As we stepped into the crawlspace utility room, we could hear a quiet, steady, rhythmic, dripping sound. This was the sound of our condensation trap in action. Because our 80-foot underground pipe was sitting deep in clay soil that registered 54 degrees Fahrenheit, the incoming 98-degree air underwent a rapid, violent thermal shock. As the air temperature plummeted inside the pipe, it instantly hit its dew point. The water vapor suspended in the air condensed directly onto the smooth, glassy walls of our Schedule 40 PVC. Because we had carefully engineered that 2% downward slope, the water did not pool. It slid down the pipe, falling directly into our buried drainage basin. We measured the discharge from our automatic bilge pump. It was evacuating nearly 6 gallons of water every 24 hours. If we had used corrugated pipe, or if our slope had been off by even 0.5%, that water would have remained trapped inside the pipe. It would have turned our fresh air supply into a stagnant, mold-filled canal. Instead, the air entering our living room was not only cooled, but it was also partially dehumidified, discharging into our home at a comfortable, steady 64 degrees Fahrenheit. But as the heat wave entered its fifth consecutive day, we encountered a fundamental limitation of soil physics, a reality that many overconfident DIY tutorials completely ignore. Now, picture this. The ground beneath our feet is a massive thermal battery, but its capacity to absorb heat is not limitless. By day 5 of continuous operation, the soil immediately surrounding the outer walls of our PVC pipe had heat saturated. Because clay soil conducts heat slowly, the continuous deposit of thermal energy from the hot incoming air had warmed the earth immediately touching our pipe from 54 degrees up to 64 degrees Fahrenheit. With a smaller temperature difference between the incoming air and the pipe walls, the cooling efficiency of the system began to decay. The discharge temperature at our indoor register slowly climbed from 64 degrees up to 70 degrees Fahrenheit. It was still significantly cooler than the 98-degree air outside, but the thermal depletion was undeniable. This proved a vital thermodynamic lesson. An earth-air heat exchanger is not a magical infinite cooling machine. It is an incremental thermal pretemperer. To maintain its efficiency over long periods, the system must be allowed to rest during the cool night hours, allowing the surrounding soil time to dissipate the accumulated heat back into the wider earth. 6 months later, the season inverted, and the natural world delivered an entirely different kind of extreme. A sudden polar vortex swept down from Canada, bringing a howling, freezing wind that drove the outdoor thermometer down to -10 degrees Fahrenheit. At these extreme temperatures, conventional air source heat pumps lose their efficiency entirely, and heating a home with wood or propane becomes a constant, exhausting struggle against freezing drafts. But we did not shut our system down. Instead, we ran our earth tube in reverse, using the ground's thermal energy not to cool, but to preheat the freezing outdoor air before it entered our home. As the -10-degree air was drawn into the intake pipe, it passed through the same 6 to 8 foot deep trench. Because the ground at that depth was still holding on to the residual warmth of the previous autumn, registering a steady 50 degrees Fahrenheit, the freezing air began to absorb heat from the pipe walls. By the time the air reached our home's ventilation system, its temperature had risen from -10 degrees up to a safe, stable 42 degrees Fahrenheit. This represented a massive thermal lift of 52 degrees, accomplished without a single watt of heating element power. Our home's primary heating system no longer had to fight to warm up freezing sub-zero air. It only had to raise the tempered 42-degree air up to 68 degrees, cutting our winter fuel consumption in half. But as the sub-zero temperatures persisted, we ran headfirst into a highly destructive physical trap: the ice plug phenomenon. During the humid summer months, our system had condensed gallons of water that drained down into our underground collection basin. But in the dead of winter, as we pulled sub-zero air into that same pipe, the freezing air passing over the residual summer moisture inside the drainage chamber created a sudden, localized flash freeze. The water inside the drainage chamber froze solid, expanding rapidly. The ice plug completely blocked the airflow through our system, and the physical pressure of the expanding ice threatened to crack our buried PVC pipes beneath 8 feet of frozen earth. If that pipe cracked, the entire system would be ruined, buried under tons of inaccessible soil. To prevent this structural disaster, we had to immediately shut down the fan and implement our emergency winter bypass protocol. We used a temporary heat tracing cable that we had pre-routed along the drainage line to melt the ice, allowing the trapped water to drain away safely. This taught us another critical safety lesson. If you plan to run an earth tube for winter preheating in cold climates, the system must be completely cleared of all summer condensation before the first hard freeze, and the condensation sump must be positioned well below the local frost line to prevent catastrophic freezing. The dual-season trial proved that our system was a highly effective engineering tool, but it also humbled us. It showed us that we cannot outsmart the laws of thermodynamics with simple shortcuts. Nature will always find the weak point in your design. Whether it is heat saturating your soil in the summer or freezing your drain line in the winter. Safe, reliable operation requires constant vigilance, regular maintenance, and a deep respect for the forces of physics. The numbers don't lie. To move past the subjective feelings of comfort, we have to look at the cold, hard data collected by our instrumentation over a continuous 72-hour test window. During our midsummer trials, we mounted digital temperature and humidity sensors at 3 critical points: the outdoor air intake, the lowest point of the subterranean pipe near the condensation sump, and the indoor registers where the air is discharged into the cabin. On the hottest afternoon of the trial, when the outdoor ambient temperature peaked at 96 degrees Fahrenheit with 60% relative humidity, the thermal transition inside the pipe was stark. At the entry point, the air was hot and heavy, but as it traveled through the 80-foot run of smoothbore Schedule 40 PVC, the temperature began to drop. By the time the air reached the 50-foot mark, the temperature had fallen to 71 degrees Fahrenheit. At the final register, the air was discharged into the home at a steady, cool 64 degrees Fahrenheit. This represents a net temperature drop of 32 degrees Fahrenheit. To understand the energy dynamics of this thermal exchange, we have to look at the volumetric flow rate. Our inline direct current blower was moving exactly 250 cubic feet per minute of air through our 6-inch pipe network, using the standard formula for sensible heat transfer, where the cooling capacity in British thermal units per hour is calculated by multiplying the volumetric flow rate by the temperature difference and a constant of 1.08. We find that our system was producing 8,640 British thermal units per hour of continuous, sensible cooling. Think about that for a second. That is nearly 3/4 of a ton of air conditioning capacity. But the most striking aspect of this data is the power consumption. A standard compressor-driven window air conditioner of similar cooling capacity requires anywhere from 800 to 1,200 watts of alternating current electricity to operate. Our low-voltage inline blower, operating on a high-efficiency brushless direct current motor, was drawing exactly 35 watts of direct current power. This yields an effective coefficient of performance of over 70. This means that for every single watt of electrical energy we put into our fan, the earth-to-air heat exchanger returned more than 70 watts of thermal cooling energy to the living space. It is an energy multiplier that conventional compressor-based systems cannot match. Furthermore, our relative humidity sensors showed a significant transition. While the outdoor relative humidity was 60% at 96 degrees Fahrenheit, the cooled discharge air entered our home at 85% relative humidity at 64 degrees Fahrenheit. Because we had lowered the air temperature close to its dew point, we successfully wrung out the heavy, oppressive moisture from the air, collecting the liquid condensation in our underground basin and venting the dry, tempered air directly into our living quarters. But here is the critical distinction that we must make at the 16-minute and 30-second mark, a limitation that every responsible off-grid designer must understand. This system cannot lower your indoor space to a chilly 65 degrees Fahrenheit on its own if the solar heat load on your roof is massive. It is not an active, closed-loop refrigerant cycle. It does not possess a thermostat that you can simply turn down to a precise digit. Rather, it acts as a highly efficient, sensible heat pre-temperer. It offsets the massive peak cooling load of your home by providing a steady, gentle baseline of cool, fresh air. It works in partnership with your building envelope, reducing the strain on your primary cooling systems and ensuring that your off-grid, electrical grid remains perfectly stable, even during the worst summer heat waves. As we stand at the indoor outlet register, feeling that steady, gentle draft of cool air that was tempered by the soil 8 feet below, we are reminded of a deeper philosophy of off-grid living. The story of the Earth-Air Heat Exchanger is not a story of finding a magical, zero-cost loophole in the laws of physics. It is a slow, methodical collaboration with the ground beneath our feet. Whether we look at the legendary clay pipe designs of Jacob Stoltzfus in Lancaster County in 1881, or the modern, computer-modeled geothermal installations of today, the core principle remains exactly the same: simplicity and stewardship. But simplicity does not mean carelessness. To build an off-grid system that is truly sustainable, we must refuse to cut corners. We must reject the oversimplified viral claims of zero-cost miracles and instead commit ourselves to the rigorous, sometimes exhausting work of safe, responsible engineering. We must test our soils for thermal diffusivity. We must grade our trenches with laser-like precision to manage condensation. And we must design our ventilation systems to maintain a perfect atmospheric pressure balance, eliminating the deadly threat of carbon monoxide backdrafting and radon gas ingress. Geothermal technology is not a shortcut. It is a deep, binding commitment to understanding fluid dynamics, soil science, and thermodynamics. As you plan your own off-grid journey, whether you are carving a home out of the rocky hillsides of the West or taming the humid forests of the East, remember that your design must respect both the beauty and the physical laws of the natural world. Protect your indoor air quality, verify your local water tables, install your safety sensors, and build a system that will keep your home comfortable, sustainable, and safe for generations to come.